Welcome to the Explainer. Today, we're going to tackle a really cool question. How can an AI learn anything without a teacher? How does it find hidden patterns all by itself?
Okay, so think about something like Spotify. They have millions of songs and millions of users. How in the world do they create playlists like Discover Weekly? It's not like they have a label for every single song that says, hey, this is perfect for a Monday morning, right? Nope. Instead, they have to find the natural groups hiding in the data, and that's the exact challenge we're tackling today.
Well, the solution to this whole problem comes from a field of AI called unsupervised learning. And that word, unsupervised, is everything. Unlike other kinds of AI, we don't give it the answers. We don't pre-label anything. Instead, we just dump all the raw data on it and say, go figure it out. Find the structure, find the groups on your own.
So how do we do that? Well, one of the most powerful and fundamental techniques for finding these hidden groups is something called clustering. And honestly, it's a powerful idea you probably use all the time without even thinking about it.
The goal here is pretty simple, but it's really powerful. You want to put similar things together. The idea is to make sure everything inside a single group is as alike as possible. And at the exact same time, you want to make sure that the different groups are as different from each other as they can possibly be. It's all about finding those natural divides.
Okay, so why should you care? Well, this isn't just some abstract idea. It is used everywhere. Think about it. Urban planners use this to find hotspots of activity in a city just from GPS data. In the medical world, it's used to automatically segment tumors in scans. And for businesses, it's a goldmine for finding customer groups you never even knew you had, opening up totally new ways to market to them.
Right, so there are a couple of ways you can go about this clustering thing. On the left, you've got what's called hierarchical clustering, which is like building out a whole family tree of your data, showing how things are related at different levels. And on the right, you have partitional clustering, which is way more direct. It's more like just picking teams for a game. For today's explainer, we're going to focus on that second one, the partitional method.
And when it comes to that picking teams method, the most popular algorithm by a long shot is called K-means. It's awesome, it's super intuitive, and it's the perfect way to really get how machines can find these hidden groups.
The whole idea behind K-means is actually built on just a few simple rules. First, every cluster has a center point, which has a fancy name, a centroid, but really, just think of it as the team captain. Second, every single data point gets assigned to the team of the nearest captain. The only catch? You, the human, have to tell the algorithm how many teams, or K, you want it to find before it even starts.
Okay, so reading a list of rules is one thing, but seeing K-means in action, that's where you really see the magic. It's almost like watching a little dance, where the algorithm slowly but surely finds the best possible groups. Let's walk through it step by step. So step 1 starts with, believe it or not, total randomness. In this case, we've told the algorithm, hey, we're looking for 3 clusters, so K is 3. The first thing it does is just plop 3 of those centers, those black circles, down in completely random spots. That's it. That's our starting guess. All right, now for the first move in our little dance. This is the assignment step. What happens is every single one of those little diamonds looks at the 3 centers and basically joins the team of the one that's closest to. So now we have our very first kind of messy version of our 3 clusters. But you can see those first guesses were not great, right? They were random. So now comes the most important part, the update. Basically, each of those team captains moves to the dead center of all the points that just joined its team. They're repositioning to be right in the middle of their new players.
And from here, we just do it all over again. The points get reassigned to the new, better positioned centers, and then the centers update their position again. This whole process, this back and forth of assign and update, just keeps going until nothing changes anymore. Once the centers stop moving, the groups are stable. The algorithm's done its job.
So let's just quickly run through that whole dance one more time, now that we've seen it. 1. You tell it how many clusters you want. That's your K. 2. It drops some random centers. 3. Every point gets assigned to the nearest center. 4. The centers move to the middle of their new teams. And 5. You just repeat 3 and 4 over and over and over until the groups settle down. That's K-means. Simple, right? But incredibly effective.
Okay, so K-means sounds pretty amazing, right? But it's not a silver bullet. It has some really important limitations you absolutely have to know about, because it makes one huge assumption about what your data looks like. And this right here shows its biggest weakness. See, K-means basically assumes that all clusters are nice round blobs. It has no idea how to handle more complex shapes, what we call non-convex shapes. Think of something like a banana or a donut. So when you give it these two intertwined crescent shapes, it can't see that natural grouping. It just tries to carve out round blobs from it, and it gets it totally wrong.
But there's another challenge, and this one is even bigger and, honestly, a little weirder. It affects pretty much all clustering algorithms, especially with the kind of massive datasets we have today. It's a spooky-sounding idea called the curse of dimensionality.
Okay, stick with me here because this is super counterintuitive. You'd think that more data, more features is always better, right? Well, not always, because every feature you add is another dimension, and that's where things get really weird. Think about it. Going from one dimension, a line, to two, a square, is a big jump. Going to three, a cube, is even bigger. Now imagine a space with hundreds of dimensions. The sheer volume of that space just explodes exponentially. Your data points get scattered across this enormous, mostly empty space. And here's the crazy part. The distance between any 2 points just skyrockets. Everything starts to feel equally far away from everything else. And if everything is far away, how can you possibly find the nearest neighbor? The whole idea of a cluster starts to break down.
So this leads us to a really interesting puzzle. If piling on more and more features can actually make our job harder and can actually hide the very patterns we're trying to find, what's the solution? How do we deal with this curse?
Well, it turns out the answer isn't just to throw away data. It's about being smarter with the features you have. The solution is a whole family of techniques called dimensionality reduction. It's all about squishing the data down to its most important parts without losing the good stuff. That allows algorithms like k-means to finally see the real patterns and do their job properly. And that is a story for another time.